All right, so I think this is running. So I'm decided to do this one on the computer. So first off, we just need to define our x and our phi. So I've got it over here. I'll copy and paste that in so you can see that. Okay, and now if I type in whos, I can see what's there. So my x is a 3 by 4, my phi is a 3 by 1. It's really important to keep track of the sizes. Number 5 is what we're looking for in the homework now. Let's see if I can find that real quick and put it up on the screen. Verify numerically that the variance of the projected data to the first basis vector, first best basis vector, first one is given by the first eigenvalue of the covariance matrix. Careful if you use the eigen command, the eigenvalues may not be ordered, I should say. Sometimes they are. Okay, good. So let's see if that is true. The variance of the projected data to the first basis vector. So first I need the basis vectors. So let's go ahead and compute the covariance matrix. So C equals covariance X. Is that right? Let's double check our sizes. Oops, I see C is a 4 by 4. Should C be a 4 by 4? No, C should be a 3 by 3. Therefore, I've got the wrong dimension there, so let me redo that. So I'm going to take covariance of X transpose instead for Matlab. It may be different for Python, but double check your sizes. That's the way to make sure that everything is working correctly. There it is. Now we have a 3 by 3. Okay, now we want to compute the eigenvectors and eigenvalues of the covariance matrix. Remember, we talked about how to do this earlier in the linear algebra section. Okay, and so I'm just going to leave the thing off so I can see what's happening. So the columns of V are the eigenvectors, and the diagonal elements are the eigenvalues. And you see that they are ordered from smallest to biggest instead of biggest to smallest. But we see here that the 3.1759 is the largest eigenvalue, and then the third column of V is going to be our basis vector. So let's just call that phi. Oh, I've already got phi. Phi. We're not going to use the other phi, I don't think. So phi equals V. You don't have to do that, but it might be easier to compare our notes. Okay, so now what I should be seeing is that the variance of the data should be equal to 3.1759 projected to the first eigenvector, right? So how do I project my data onto phi? Well, I can take, let's see, should we go ahead and mean subtract? Mean column is equal to mean of x2, and then take xm equals to x minus mean column, and I can double check everything. xm is 3 by 4, that is the mean subtracted data. In fact, I can take a look at it. Good. Oh gosh, I'm giving away all the problems. How do I how do I do the projection now? V transpose. Gosh, this is so fun. Are you guys having a good time? So what does that represent? This is the projection of the data onto phi1 as a 1 by 4 vector, right? That's what we said. And so it's the variance of this data that we're checking. Variance of phi transpose times x. And we get, what do we get? We get 0.1574. Is that what we should keep getting? Let's double check. Okay, I see the error. Did you guys see it? Were you yelling at me about it? If I go up, I'll see the error. Keep going up, and see I'll see the error. Keep going up. There it is. Do you remember what we said? It's the third eigenvalue, or third column of V. That's our phi. So let me redo that. Do you think it's going to work this time? Well, in theory it should. Where are we? Phi. There it is. Okay, and now we'll just compute the variance again. Where are you, variance? Did I pass it? I'll just type it in. Okay, oh, what else did I do wrong? I forgot to... Boy, I did all kinds of things wrong in that last command. You guys should have been here to tell me. There it is. Right? That is our variance, and that is the third eigenvalue. And so we are done. Whoops. What happened there? Where did you guys go? Let's see if I can escape. Okay. So that's the solution to the next one. I think I'll stop here and then we'll take a look at the next one.